Hello guys, we want to start our 13th video lecture today. So in this video lecture, I want to talk about second translation theorem, and then we want to talk about inverse form of second translation theorem, and at the end we're going to talk about alternative of second translation theorem. So second translation theorem says that if Laplace transform of ft is equal to fs and a is greater than 0, then Laplace transform of ft minus a times ut minus a, which is unit step function, is equal to e to the power of minus as times fs. So now we have an example here to see how we can use second translation theorem to find Laplace transform of the function. In this example, you want to find Laplace transform of t minus 2 cube times ut minus 2. If just we compare this function, t minus 2 cube times ut minus 2, with the formula that we have in the second translation theorem, we can see that ft minus a that we have in second translation theorem, so it's here we have it's equal to t minus 2 to the power of 3, and ut minus a in second translation theorem, so here we have ut minus 2. As a result, so a is equal to 2, and here if we have ft minus a is equal to t minus 2, as a result, t minus 2 cube, as a result ft is equal to t cube. Now we have to find fs. Fs is Laplace transform of ft, so fs is equal to Laplace transform of ft, which is Laplace transform of t cube, so it's equal to 3 factorial divided by s to the power of 3 plus 1 is 4. So it's equal to 6 over s to the power of 4. As a result, now we can say that based on second translation theorem, Laplace transform of t minus 2 cube u t minus 2, it's equal to e to the power of minus as. So a we already found it is equal to 2, so it's equal to e to the power of minus 2s times fs. We already found fs here, so it's 6 over s to the power of 4. So we could find Laplace transform of this function using second translation theorem. Now we know second translation theorem, we want to talk about inverse form of second translation theorem. So based on these theorems, so when we have, then you're going to find Laplace inverse of e to the power of minus as times fs. So it's equal to ft minus a times ut minus a. U is unit step function, so in this case ft is equal to Laplace inverse of fs. So now we can see how we use inverse form of second translation theorem to find Laplace inverse of one function. Let's see this example. In this example, we want to find Laplace inverse of e to the power of minus 2s over s squared times s minus 1. If you just compare this function, e to the power of minus 2s over s squared times s minus 1, with the function that you have in inverse form of second translation theorem, so you can see that this Laplace transform is equal to Laplace inverse is equal to Laplace inverse of e to the power of minus 2s times 1 over s squared times s minus 1. So now here we have e to the power of minus 2s. In the formula we have in the formula that you have e to the power of minus as. Here we have e to the power of minus 2s. As a result, you can say easily A is equal to 2. And here we have fs, here we have 1s squared plus 1 over s squared times s minus 1. So as a result, fs is equal to 1 over s squared times s minus 1. So in order to solve this problem, inverse form of second translation theorem says that it's equal to ft minus a times ut minus a. We know that it's 2, but we have to find ft minus a. How we can find ft minus a? First, we can find ft. ft is inverse of fs. As a result, at first I find ft. ft is equal to Laplace inverse of 1 over s squared times s minus 1. So I have to use a partial fraction to solve this to find Laplace inverse of this function. So if I use partial fraction decomposition, this function is very easy, so you can easily find it's equal to Laplace inverse of minus 1 over s minus 1 over s squared plus 1 over s minus 1. Using partial fraction decomposition, you already know, so you can easily find these three partial fractions. As a result, ft is equal to Laplace inverse of minus 1 over s is minus 1. Laplace inverse of 1 over s squared is t minus t. Laplace inverse of 1 over s minus 1 is plus e to the power of t. So now we have ft. As a result, based on inverse of second translation theorem, Laplace inverse of e to the power of minus 2s times 1 over s squared times s minus 1, it's equal to. Now here we have ft, but we have to make ft minus a. A is 2, we have to make ft minus 2. So here we have a constant function. If you have a constant function, ft and ft minus 2, they are the same because we don't have any variable here. As a result, we have minus 1 times ut minus a. So it's minus 1 times ut minus 2. So we have ut minus 2. It's for the first part of ft. Then we have minus t. It's ft. As a result, ft minus 2 is minus t minus 2 times ut minus 2 times ut minus 2. And at the end, so we have ft is equal to e to the power of t, but we have to find ft minus 2. So in fact, it's equal to e to the power of t minus 2 u times u t minus 2. So we could find Laplace inverse of this function using inverse form of second translation theorem. You know about partial fraction of these fractions, so but in case you forgot, so just to say it's a note how we can find partial fraction of 1 over s squared times s minus 1 is very simple. So we have to look at the denominator. So we have s squared. As a result, based on the table that we have, it's 1a over s, b over s squared, and we have s minus 1, so it's c over s minus 1. So then if add them together, the fractions, so we have a times s minus 1 plus b times s minus 1 plus c times s squared over s times s squared, sorry, over s squared times s minus 1. So now 1 is equal to, because this fraction is equal to this fraction, denominator is the same, numerator should be the same. So it's equal to a times s minus 1 plus b times s minus 1 plus c squared. So now just plug s equal to 0. If you plug s equal to 0, left hand side is 1, right hand side a times 0 gone, c times 0 gone, so we have minus b. As a result, b is equal to minus 1. If you plug s equal to 1, a times 0 is gone, b times 0 is gone, so c is equal to 1. And if you plug one random number like s to the power of 2 in the left and right side of the equation, so you can find a equal to minus 1 as well. So as a result, so now you have partial fractions of the function, so you can easily use the table of Laplace transform to find Laplace inverse of 1 over s squared times s minus 1. So let's go through the next part. In this part, you want to talk about alternative of second translation theorem. So based on this theorem, so it says Laplace transform of gt times ut minus a is equal to e to the power of minus as times Laplace transform of gt plus a. Now we solve one example to see how it works. Imagine I want to find Laplace transform of t squared ut minus a. If you just compare these function with alternative of second translation theorem, we can see that gt is equal to t squared and ut minus a in our example is ut minus 2. As a result, a is equal to 2. So I can use alternative of second translation theorem to find Laplace transform of t squared ut minus 2. So based on this alternative, so it's equal to e to the power of minus as, a is 2 minus 2s, Laplace transform of gt plus 2. Or it's equal to e to the power of minus 2s, Laplace transform of g is t squared, gt plus 2 is t plus 2 squared. So t plus 2 squared. So now I just expand t plus 2 squared. So we have e to the power of minus 2s, Laplace transform of t squared plus 4t plus 4 is equal to. So Laplace transform of t squared is 2 over s cubed. So it's equal to e to the power of minus 2s times 2 factorial is 2 over s cubed plus Laplace transform of 4t is 4 over s. So 4 e to the power of minus 2s over 1 squared. Laplace transform of 4 is 1 over s plus 4 e to the power of minus 2s 1 over s. So we could find Laplace transform of this function using alternative of second translation theorem. So we want to solve our last example in this lecture. In this example, we want to find Laplace transform of t minus 2 squared times ut minus 3. In the second translation theorem, we had Laplace transform of ft minus a times ut minus a, it's equal to e to the power of minus as times fs. But if you compare our example, second translation theorem, here is you have ft minus a, here you have t minus 2 squared, here you have ut minus a, but in the example you have ut minus 3, we don't have ut minus 2. As a result, we cannot use second translation theorem, we have to use alternative of second translation theorem. In fact, in our example, we want to find Laplace transform of t minus 2 squared ut minus 3. So I just expanded, so it's equal to Laplace transform of t squared minus 4t plus 4 ut minus 3 it's equal to Laplace transform of t squared ut minus 3 minus 4 Laplace transform of t ut minus 3 plus 4 Laplace transform of ut minus 3. Now for each term, for example, for t squared ut minus 3, we have to use alternative of second translation theorem. For t times ut minus 3, we have to use alternative, and for the third part, 4 times ut minus 3, so again we have to use alternative of second translation theorem to find Laplace transform of our function in this example. So for the first part, based on alternative of first translation theorem, we have it's equal to e to the power of minus as is minus 3s. Laplace transform of t plus 3 squared. For the second one, we have minus 4 e to the power of minus 3s. Laplace transform of t plus 3. And for the last one, so we have 4 times e to the power of minus 3s. Laplace transform of 1 is equal. So I just expand this term. It's equal to e to the power of minus 3s Laplace transform of t squared plus 6t plus 9 minus 4 e to the power of minus 3s Laplace transform of t plus 3 plus 4 e to the power of minus 3s Laplace transform of 1. It's equal. If I just factor out e to the power of minus 3s, what's left? So here we have t squared. Laplace of t squared is 2 over s cubed. Laplace transform of 6t is equal to 6 over s squared. Laplace transform of 9 is equal to 9 over s. Minus 4 times Laplace transform of t is 1 over s squared, so it's minus 4 over s squared. Laplace transform of 3 is 3 over s, so we have to multiply by minus 4, so it's minus 12 over s plus 4 times Laplace transform of 1, which is 4 over s. So we could find Laplace transform of this function using alternative of second translation theorem.